In this segment, I want to talk about processor design and evolution, including covering how processors are actually made, the changes in technology that have occurred over the years, as well as changes in packaging and power consumption. Now, when most people think of a processor, they think of a chip like this, for example, this Intel Core i-series processor that I have here. Now, when most people look at this, they say, oh yeah, that's a chip, but what they're really looking at is the package. What I'm really interested in, what we're going to talk about more here, is what's inside the package. Now, in this cutaway view, I have a magnified image of one of Intel's latest Core series processors, and underneath this metal cap, you can see the actual processor die. The die is the actual circuit that comprises the processor. Now, this circuit is incredibly complicated. These circuits can have upwards of 1 billion or more transistors in them. So it's an incredibly complicated circuit. In fact, I would have to say the processor is one of the most complicated components that is manufactured by man today. So let's look at how these things are actually made. Well, processors, the raw material that go into processors is silicon. And I have an example of a chunk of pure silicon right here. Now, silicon is the second most abundant element on the planet. The only thing that we have more of is oxygen. One thing, though, silicon is rarely found in any kind of a pure form. It's mostly mixed with oxygen in the form of silicon dioxide, which most of us know as quartz or sand. So, in fact, sand is mostly silicon. So, many times you've probably heard that, electronic circuits are made out of sand, and that's largely true. So what happens is we take the sand, melt it down, and put it through a purification process until we extract the 99.999% pure silicon. Now, even that's still not ready to make chips out of. We need the silicon not only to be pure, but to be in the form of a crystal. So what happens then is the pure silicon is melted in a vat, and a seed crystal, like the one I have here, is dunked into the vat of molten material. It's slowly turned and then pulled out. Now, if you imagine this vat of molten material, it's kind of like melted glass. It's sort of thick and taffy-like. And as the crystal begins to pull out, some of the material sticks to it and begins to harden. So what happens is this seed crystal pulls out of the vat, and you can see a bunch of material sticking to it. And they pull at first rapidly until we have a very thin stem forming, and then finally more slowly until a wider and wider crystal begins to emerge from the vat. This is an example of a pure silicon crystal that I have here that was grown in one of these vats. As you can see, the shoulder of the crystal gets wider and wider as it is pulled out. This is like millimeters per hour. It's a very slow process. Now, once the crystal reaches the diameter that is intended to be, then the process speeds up a little bit. It's pulled out a little bit more quickly until basically what we have is like a cylinder. Imagine a cylinder of this crystal material being pulled out of this vat. Once the cylinder has reached its final length, which is usually a couple of feet long, then the pulling process goes more quickly and we end up with a tail. They want to actually have a sort of a gradual pull-out of the material from the vat to prevent any kind of thermal shock. Now, the tail on this crystal is very short. It's very short here, as you can see. In fact, this was an aborted crystal process. Normally, the main body would be not just an inch here, but would be several feet tall. This, in fact, is here as an example of a tail of a more complete crystal. So if you can imagine, this thing was several feet tall, and then this was the tail that's basically cut off and is considered waste. The head and the tail are then chopped off of this crystal. So now what we have is this cylindrical crystal of silicon. Head and tail are cut off. This is then put into, it's ground so that it's perfectly round, and then it is put into a saw that cuts it into thousands of plates called wafers. I have an example here of a wafer that was cut from one of these crystals. You can see that it's round and is very thin. It's less than a millimeter thick. Thousands of these usually come out of one single crystal. Now, the wafer would then be polished to an absolutely flat surface, better than most mirrors, a mirror polish. And then what we have is called a wafer, and this is the sort of the raw base building material for making chips. Now, what happens is the wafer is put into a process that's a photolithographic process. We take a mask, which is, you could call it like a negative. We shine a light through it, and we literally etch the various dye into the wafer. I'm going to show you an example here. This is an example of a wafer that has 177 finished die etched into it. As you can see, they're just one after the other, rows and rows and rows of them. One mask was used to, to produce this, or I should say one collection of masks, because each of these die is not just one image that's put on this wafer. It's a stacked series of images, usually 20 or more layers. And through the photolithographic process, material is coated onto the wafer, then it is etched with the ultraviolet laser, then portions are washed off, and we literally have like a cake building process, a layer upon layer upon layer, until this very complicated series of circuits is assembled. Then, once the wafer is complete, the individual die are then cut out of it. So we end up with individual square processor die. Now, a typical die, might be something on the order of these sizes here. I have I made up some pieces of paper that are about the size of most modern processor die. They can be anywhere from usually 10 millimeters to 20 millimeters square on each side. Some are more rectangular, some are square. Okay, so now we've seen the basic, building process of making processors, but let's take a look at how this technology has changed over the years. Processors have been made for nearly 40 years now. The first one came out in 1971. What was different, from then to now? Well, a couple of things that have changed. One is the size of the wafers. This is an example wafer from around 1973-74 when they were 3 inches in diameter. As you can actually see, this one has a series of chips imprinted on it. This one was never cut. The chips were never cut out into the separate die. Now, wafer sizes have increased over the years. Most recently, we had a transition from 8-inch wafers to 12-inch wafers. And what that means is that the wafers that are being used for most chips today are 12 inches in diameter. Now, as the wafer size increases, the number of chips that can be imprinted on them go up. For example, this wafer image that I have here was actually originally an 8-inch wafer. And with the 8-inch design, 177 separate chips could be etched or fit onto this wafer. Well, when this was increased to 12 inches, they began making the same chips on a 12-inch wafer. They were able to make 449 chips on the same exact wafer. So in the same amount of time, they are now making, nearly or more than twice as many chips. As the wafer size went from 8 inches to 12 inches, the surface area grew grew 2.25 times. So we can have literally more than double the number of chips being produced. So these are some of the technology changes that have happened. The wafers have gotten bigger. One other thing has been going on, though. The componentry that goes into each of these die has become smaller and smaller. When processors were first being made, the very first processor in 1971 had components spaced 10,000 nanometers apart. That's 10,000 billionths of a meter. Today, we are making chips with the componentry spaced only 32 nanometers apart. That's hundreds of times more dense, more components fitting into the same space. So while the die of a processor has remained relatively the same since about when the 486 came out in 1989 to the present, the actual individual size of the processor chip within the chip has remained the same. But the number of components has gone up tremendously. The 486 had 1 million transistors on it. Today we have processors approaching 1 billion transistors. So, as you can see, the two big changes that have occurred in processor manufacturing is going to larger and larger silicon wafers on which we etch the chips. And then each die, while the die has remained relatively the same size over the years, more and more components are being crammed into them. Now, let's take a look at sort of a timeline of processors over the years, PC processors especially, and look at how not only the processors have changed, but the packaging and cooling issues as well. I have assembled here nearly 40 years worth of processor history, I thought we could take a look at this. Now in 1971, the very first processor that was introduced by Intel was called the 4004, and I have an example of that right here. Now this is not an actual 4004 chip, but it looks like one. Real 4004s are actually quite rare and considered to be collector's items today. But this chip is exactly the same size, shape, number of pins, and everything as the original. Now on it, I have a little white square. That represents the actual die size of the original 4004, the first processor. As you can see, it's pretty tiny by today's standards. Now next to it here, I have an Intel 8088 processor. Now this processor was introduced in 1979 and is the first PC processor. The IBM PC came out in 1981, and this processor actually came out of an original IBM PC motherboard. The original 4004 ran at up to 3/4 of a megahertz. That's 3/4 of a million cycles per second. The original PC ran at just under 5 megahertz. Technically, it was 4.77 million cycles per second. Now, after the first PC came out, the next processor to be released was the 286 processor. Now the 286 came out in 1982. I have 3 different examples of 286 processors here. They are noted by, they're just a different physical configuration. This first one, this uses pins that plug into a socket. This is a different design which uses pins around the edge of the chip. And then this one was one where it had no pins. The pins were actually in the socket on the motherboard, and there were just lands around the chip. Now what's interesting is that just in the last few years, this type of packaging has returned, and most of Intel's processors now use this land grid array, they call it. So at this point, processing speeds went up to about 10 to 20 megahertz. Now here we have a 386 processor. The 386 came out in 1985. And this had about 300,000 or so transistors on it. So the transistor count had been going up. We had started out around 2,000 in the first processor. We went to 30,000 in the first PC processor. We have about 130,000 in the 286, and now nearly 300,000 approximately in the 386 processor. Now the 386 is also known as being the first 32-bit processor. What's interesting is that even though that chip came out in 1985, we didn't really have 32-bit operating systems until a decade later, when Windows 95 came out. So sometimes the processor technology is ahead of the software that actually supports it. Next, we have an Intel 486 processor. The 486 came out in 1989, and this was the first processor to have over 1 million transistors on it. It was about 1.2 million transistors, actually. This also was the first processor that began this, several changes happened in that processor. One, it was the first processor that had built-in cache memory. And that was sort of a revolutionary breakthrough because processing speeds had been exceeding the speed of memory, memory chips, at least affordable ones. So by building memory into the processor, it sort of brought along its own little high-speed portable cache buffer of memory, which made things work incredibly faster. So the 486 was a breakthrough. Then we have here the 586 processor, which really wasn't called a 586, it was called a Pentium. The first Pentium came out in 1993 and had just over 3 million transistors on it. The Pentium was also, like the 386 and 486 before it, was a 32-bit processor. Now, that concept of cache I was telling you about, yes, the Pentium also had the cache built into it, but this was what we call level 1 cache. During those times, level 2 cache was still found on the motherboard, and therefore it ran at slower motherboard level speeds instead of higher or faster processor level speeds. So the next processor would change this radically. This was called the Pentium Pro, which is right here, which came out in 1995. Now the Pentium Pro was really a revolutionary chip. For one thing, it's huge. It's physically probably the largest single chip I've ever seen. And the reason is because there's actually not one chip in there, there's 2. This, in fact, represents the actual die of the Pentium Pro processor, and if I set it on here, you'll see why this chip was rectangular, because there were basically 2 chips side by side. One of them is the actual processor chip, and it has its own built-in level 1 cache memory. The other chip next to it is a level 2 cache memory chip. Now prior to this, the level 2 cache had been on the motherboard. Now it was part of the processor, but it was still a separate chip. Now this dual chip in a package processor was very expensive to produce, so it wasn't very popular because it was expensive. So Intel was working on the problem of how can they make this type of a chip with the cache built into it less expensive. Well, what they came up with was the concept of a circuit board as a processor. Now this is actually a Pentium 3 processor, but the Pentium 2 and 3 both did this. In fact, these are really P6 or 686 processors, just like the Pentium Pro. And what we have is the actual processor chip here and then cache memory alongside of it. And what this allowed Intel to do was to literally buy cache memory chips from third-party suppliers, like the ones on this are actually from Samsung, and integrate them into a circuit board. Now this type of a board would plug into a slot. Now I think Intel was possibly a little vain about this. They didn't want you to see that they were using other companies' cache memory chips on here. So what they did in the Pentium 2 packaging was they built it into a plastic case. So this little circuit board is in this thick plastic case, has a heat sink built onto it, and in fact they even have a picture of the die of the processor on the side. This was the first processor that I knew of that featured what I would call decoration. The Pentium 3 was really the same thing. The Pentium 3 was just an enhanced version of the Pentium 2 processor. Now the Pentium 2 came out in 1997 and the Pentium 3 came out in 1999. All of these continued that technology of building the level 2 cache into the chip, but it was separate chips. It was a multi-chip package. Well, finally, both Intel and AMD created small enough transistors. The process had gotten tight enough to where they could pack the level 2 cache chips into the main processor just like the level 1. Now in continuing this evolution, talking about processor packaging, most of the time when a processor is made, you don't actually see the die. It's covered up. Well, some chips were made where you did see the die. I showed you this Pentium 3 and you can actually see the raw silicon die on top of this chip. That's the actual silicon base of the processor. Now it is flipped upside down, so the circuits themselves are not visible. They're turned around. But still, that's the raw silicon die. Now there was a problem with this design that when you attached a heatsink to it, it's basically perched on this little pedestal of silicon, and if you put pressure on it a little bit too much to one side or the other, you could crack it. Silicon is like glass. In fact, here I have a piece of a wafer that I broke earlier, and it shatters like glass. So the shards flying everywhere. The edges are extremely sharp. It's very brittle. So what would happen was when you would put a heatsink on a chip like that, and here's an example from AMD. This is a AMD Athlon processor with the raw processor die sitting right in the middle of the chip there. If you put pressure on it, it would crack the die. What AMD did was put rubber pads around each of the four corners to try to mitigate that problem, but still it was happening all too frequently. So in more recent designs, both Intel and AMD have put covers over the processor die. This is an example of a Pentium 3 that has a couple of changes. Number one, the level 2 cache, which used to be separate chips. These are both Pentium 3s here. The level 2 cache is now built into the processor die, and then the die is now covered with a metal heat spreader. And they call this a heat spreader because it helps spread out the heat. It gives more surface area for the heatsink to attach to and dissipate the heat from the processor. Also protects the die, the raw silicon die, from any kind of damage. So these are much more durable. Okay, now we'll move on. The Pentium 4 processor, which I have an example of right here. Right here. This is a Pentium 4 processor. That came out in the year 2000. Also in 2000, we had the first processors that hit 1 gigahertz in operation. That was kind of an important level of speed. From 0 gigahertz to 1 gigahertz, it took 28 years. What's interesting is it only took something like 18 months to go from 1 gigahertz to 2 gigahertz. But so this was the Pentium 4 processor. Now, in 2003, AMD came out with a revolutionary new chip design. This was called the Athlon 64. This was the first 64-bit chip. Remember I said earlier how the 386 was the first 32-bit chip? Well, all of the chips from the 386 up through the Pentium 4 were mostly 32-bit designs. AMD, in this case, took the lead from Intel and created the first 64-bit design. And it was Intel who ended up copying this design and integrating it into the Pentium 4 and some of their other new Core series processors. So we now have 64-bit processing technology where the chip can operate on 64 bits of data at a time. So this was the Athlon 64, came out in 2003. Now it's interesting that it wasn't really until 2009 when Windows 7 was released that we had what I consider to be a mainstream 64-bit operating system. Yeah, there were 64-bit versions of Vista and Windows XP, but they were not what I would consider completely mainstream. Windows 7, on the other hand, is really the software jump to 64-bit. I think we're going to see most systems running in 64-bit mode with Windows 7. Okay, now, continuing on, this is an interesting chip here. This is a Pentium D processor, which was the first dual-core chip. See, up until this time, processing speeds had increased and increased from, under 1 megahertz up to over 3 gigahertz. And in fact, 3.8, nearly 4 gigahertz. But what was found was that we couldn't keep increasing speeds because heat production was going up tremendously. So rather than increase the raw speed of one chip, they came up with the idea of putting multiple chips in the single processor package and basically have multiprocessing. So we could run, we're running multiple programs at one time, and now we have multiple chips to run these programs. So we effectively have a faster system. First we had dual core, now we have quad core chips. This last processor I have here is one of the Intel's latest Core I series, and this is a quad core chip. There are 4 chips in here. Now the first dual core chips were actually 2 single cores mounted side by side under the little heat spreader there, and just likewise the first quad core chips were 2 dual core chips mounted side by side. But as the processor manufacturing had evolved, they now make both dual core and quad core chips all on the same die. So as we've seen, the processors have evolved tremendously over the years in their physical packaging. We had what started out as very small chips. We went to larger chips. We went to even cartridges, if you want to call them that, because of the extra cache. But now the concept is to bring everything back onto the single die, and now even putting multiple cores. Now I thought we'd take another look at the cooling of these processors. Over here I have an example of the evolution of processor cooling over the years. Now, when the first PCs came out in the early 80s, they didn't even have heat sinks on the processor. Today, you wouldn't think of having a processor without some type of a cooling device mounted on it, but up until, in fact, the 286 and even early 386 systems, there were no heat sinks used on processors. The processor could just ran cool enough and only used a few watts that it wasn't a problem. But when we started getting past 33 megahertz, when we went to like 66 megahertz, 100 megahertz and faster, we started to require cooling. This was what was used on some of the early processors that required a heat sink, and as you can see, it's just a passive metal radiator. No fan or anything. There was enough airflow in the system to cool it. When we got to 200 megahertz, we needed bigger passive heat sinks. This was for about a 233 megahertz processor. But when we went past 233, we found that the airflow in the system wasn't sufficient. You either need a really large, metal heat sink, or you could use a smaller one and put a fan on it. So what happened was, instead of having something big like this, we had something smaller, but it had a fan on it. So this was around a 200 to 300 megahertz processor cooler. As we went up to 400 and 500 megahertz, the processing coolers got bigger, the fans got bigger. Over here, we're up to 1 gigahertz, 2 gigahertz, and then 3 gigahertz and beyond. As you can see now, what has started out as just a small passive little heat, cooling device is now a massive finned assembly with a large fan. Now you can tell that sometimes in many of the newer heat sinks, they also use a copper core. Copper is one of the best conductors of heat, much better than aluminum and many other metals. In fact, a lot of processors are now, or heat sinks, I should say, are made using copper as part of the core. So as you can see, we've had a lot of changes occurring in processors over the years. They've gone from very small chips to, very large chips, cartridges. Now we have multi-core technology. The heat sinks to cool these devices have grown in size and complexity over the years. And all of this has taken place in the last 40 years since the processor first came out. All right, in this segment, I wanted to prepare the case for the build. Now, this is pretty much the case I purchased. It's the Enermax Vostok. It's just as I received it, and it's really not ready for me to use. I need to make some changes to the case and maybe do some upgrades in order to get this ready for the system that I'm going to build. Number one, I'm going to take out these quick install no-tool drive mount brackets, because I'm going to use actual screws to mount the drives. I don't like these. They don't hold the drive securely enough for me. Now the case does come with an assortment of screws, which is nice. Most cases do. If they don't, you'll need to procure some screws. You can buy usually kits from different suppliers. This case also came with a fan and some other components, but we'll get to that. Now, in order to continue getting the case ready, I'm going to take out the power supply and remove the front panel. Now, in order to do that, I'm going to lay the case down on its side. Now, even if I wasn't going to replace this power supply, I'd be removing it just so I could get easier access when installing the motherboard. But in this case, I am going to replace the power supply because it's not adequate. It's not adequate for the system I'm going to build. It doesn't have enough connectors, doesn't have enough power output, so I'm going to take the power supply out. It's secured by 4 screws on the back. I'm going to simply remove them and take the power supply out of the system. Okay, now that the screws are taken out, I can remove the power supply and put it to the side for now. Okay. Now, I'm going to take the front panel off so I can gain clearance for installing things like a front fan, disk drives, and other things. In most chassis, to remove the front panel, you simply push from the bottom, push outwards. Sometimes you might want to look to make sure there are no clips that you have to release on the inside. This one you just push from the bottom, and the front panel comes off. Now I have to snake out these cables. And now we have the front panel off. So I'm going to set that off to the side here. Okay, and then finally, I'm going to remove the other side panel. Most chassis you can remove, one side panel in order to install the motherboard. But if you can remove the other side panel, you get much more access for putting screws into the drives and things like that. So I'm going to take that panel off here. Okay, now we have a case really ready for me to begin assembling. It's as bare as possible. I've got the easiest access to everything. Now, a couple of other points to make. I said I was going to use a different power supply, so that's something you need to consider in advance. If you're going to use a different power supply, make sure you have it. I'm also going to use a different fan. Traditionally, the fans that just come with a case, even though this is a 120 millimeter fan, which is nice, it's a little bit noisier than I would like. It's also not necessarily a dual ball bearing fan or a hydrostatic bearing fan. So what I recommend is purchasing higher quality fans in order to install in the case when you assemble it. So at this point, we're ready to continue the build process by installing the motherboard and other components. Okay, now I'm ready to install the disk drives and the cooling fans. Now, I had mentioned previously that because I'm going to be installing 4 drives in a RAID 1.0 array, with 4 drives in close proximity at the front of the case, you can get a little bit of heat there. So I'm going to add a cooling fan to the front of the case. I'll also install the cooling fan into the bracket in the back of the case. Now, let's do the front fan first. In order to do that, I'm going to take a 92 millimeter fan that I had purchased separately, and I need to make sure that I've got the airflow flowing into the case in this front fan. So the arrow direction is this way, and I'm going to set it into place and use some of the fan screws that came with the case in order to secure it. Okay, all the 4 screws are now securing the front fan to the case, and I'll snap the back fan into the bracket. Now again, I want to look for the directional arrow. In this case, I want to make sure that the air is blowing out the back of the case. So that would be this direction. And since this fan has, this case has a nice bracket, I can simply click the fan into place into the bracket. Okay. Okay, the fans are secure. Now you would run the cables to the motherboard, plug them in. Like so. Later on I'll worry about dressing the cables, that is, making sure they're out of the way of any other components and things like that. At this point I'm just getting them plugged in. Okay, now we're ready to install the disk drives. Now I'm going to mount 4 disk drives here and then an optical drive up here. I'm going to start by mounting the hard disk drives. Now I'm going to take my first drive. Now I mentioned in another segment that these drives came with the limiting jumper installed. That is, these are 3 gigabit per second drives, but they came with a 1.5 gigabit per second limiting jumper in place. So I'm going to remove the jumpers from these drives. Now, I'm going to use a little tool to help me extract that jumper. They're very tiny little jumpers. You might want to save them just in case you need them again if you are going to install these drives in a system that doesn't support the 3 gigabit per second operation. Okay, now those jumpers are removed. Now we're going to do a mount of these drives in place. Okay, and you want to slide it until the screw holes line up, and then begin inserting the screws. So what I'm going to do is I'm going to slide all of these drives into place and install all the screws, and then we'll see what it looks like when it's complete. Okay, there's the last screw for the hard drives. I've now got 4 hard drives mounted and 1 optical drive, and I used 2 screws on either side of the drives, which mounts them very securely and also makes the case more rigid and improves thermal transfer between the drives and the case. So anyway, those are all mounted. Now I need to cable up the drives, and then I can finish install the power supply. Now all of these drives are SATA drives, so I've got 4 cables for the hard drives, and I've got 1 extra cable for the optical drive. So they are going to plug in here. Now, this motherboard has these side-mounted SATA ports, which I don't really like. I prefer them to be, plug in straight from the top. But this is how a lot of them are. Good thing that the back panel comes off of this case. because it makes getting to this a lot easier. So I'm basically going to connect the 4 hard drives and then the optical drive cable. So I'll start with the first one here. Get all these cables plugged in, and then we'll connect them up to the drives. There, I've got the last cable plugged in. All the drives are now connected to the SATA ports on the motherboard, as is the optical drive up here. As you can see, again, being able to remove the back side of the case really helps with routing these cables, getting them out of the way. It's going to make for a very neat appearance on the front side, and very clean routing. So now, at this point, I need to install the power supply. So that's going to be next. Now, in order to do that, we have to lay the system down, get my power supply, which I have here. I'm going to be using a 510 watt PC power and cooling supply. And I'm going to set it into the case. Sure I've got it the right orientation. And get it to line up with the screw holes, and then I will put in the screws. Okay, the power supply is now secure. Now at this point, I've got to route all these power supply cables. And it's easiest to do that with the system laying down. Now I'm going to need to plug in the main power, which, whoops, I have right here. I have the CPU power. I've got auxiliary power, let's see, 4 video cards, which is over here. And I've got the drive power. So I'm going to go ahead and get all these connected up, and then we'll see what that looks like. Okay, there. At this point, I've connected all of the power to all of the disk drives, including the hard drives and the optical drive. I snapped the front cover plate back on the system and ran the front panel USB and audio connectors to the motherboard. You can see those here. Here's the USB connection, the front panel connection. Now that was made a whole lot easier because I had replaced those multiple little pin, connectors with a single individual connector. The USB was a single individual connector, and the audio, the front panel audio, was a single, individual connector, not a bunch of little tiny pins that you had to try to get on there. Also, I used my trusty zip ties to tie up some of the cables to keep them away from the motherboard. I like to have everything as open, as clear as possible, unobstructed airflow through the system. As you can see, the wiring turned out, very nice and neat. A lot of it is kind of hidden on the other side here. Here's the hard drive and optical serial ATA cables, and here's where the front panel cables came in through the case. So it's so nice to be able to take this back panel off and be able to route the wires like this. Okay, now at this point, we only have one thing left to do, and that's to install the video card. So that's going to basically go into the number 1 PCI Express X16 slot right here. So all I have to do is remove the card bracket holder from the back of the PC here and pop the card into its slot. Now, well, let me first get that screw out of there. Take that off. Okay, now I wanted to make a point about this video card. I mean, I like a high-powered video card as much as anybody, but I can't stand the noise and failure-prone small fans. A lot of video cards have small fans on them, and they very easily clog up and are very failure-prone. So this is what's called a passive heatsink cooled video card. It has a heatsink on it, but it uses no fan. So it relies on the cooling in the system to pull enough airflow over this to keep it cool. Now, because it is a no-fan video card, it doesn't require extra power. So although this power supply had extra, PCI Express video power connectors, it could drive a very high-powered video card, this will not need that. So basically, all I'm going to do now is install the card in the slot. Now, as you can see, I've removed the bracket from the slot here, so the back of the machine, so I can line this card up with the slot, make sure it goes in straight, and pop it into place. Now, once it's installed, I can then lock it down with the card holder here. Okay, so now the video card is secure, and basically at this point the system is complete. All I have left to do now is to put the side covers on, the front and back side cover, and hook up the power. Then basically I would run the BIOS setup, set up the RAID array through the Intel BIOS, and then begin loading my operating system. So this PC is pretty much ready to go. In this segment, we're going to install the processor into the motherboard, the heatsink onto the processor, and then we're also going to install the RAM. Now, installing the processor and heatsink is probably the most difficult single part of building a PC for the novice person. But it doesn't really need to be that difficult. You'll see exactly how it's done here, and I'll give you some tips and tricks along the way to make it easy and a little less intimidating. Now, the one problem with this is that in most situations, when you go to install the processor and RAM, the motherboard already has to be mounted in the system. You can't really install the processor and the heatsink with the motherboard out of the system because you have to put a lot of pressure, and particularly when you install the heatsink, and it's normally the best if the motherboard is already installed. Well, that's where in the other segments I've talked about having a chassis that uses a removable motherboard tray, because that means you can install the processor and heatsink and memory with the motherboard essentially out of the system without the confines of the case around you, making it difficult to see what you're doing and get your hands in there and everything like that. Well, I save trays, motherboard trays from cases that I've discarded just for the purpose of installing processors, heatsinks, and RAM to make it easy. Then once all of this is installed, I can then load the motherboard into the chassis with everything ready to go. So at this point, if you don't have a removable motherboard tray, you'll have to install the motherboard first into the chassis, then complete these steps that we're going to do here. So now we're going to install the processor. This motherboard happens to have a socket LGA1366. That stands for Land Grid Array 1366 pins. Now what that means is that the pins are actually in the socket, not on the processor. If I take, for example, the processor looks like this. It comes with a protective cover over the back of it, and if I take that cover off, it just snaps off. You can actually see the lands on the back of the chip. Now, these are just basically gold spots, gold contacts. There's no more pins. Older processors, or other processors in some cases, use individual pins there instead of the lands. In this design, the pins are actually in the socket. Now, in order to get this ready to be installed, I have to remove the tension on the load plate. And what we have here is called the load lever, which presses down on the plate that will eventually hold the processor in the system. So I'm going to move this lever over to the side, lift up what's called the load lever, and then I'm going to lift up the load plate. And now I'm going to remove the plastic protector that comes in the motherboard. This protector protects all the tiny little pins which are in the socket. There's, as I said before, 1,366 fine, very tiny pins in the socket, and you do not want to touch them. Just the slightest touch, snag it with a little bit of cloth, something like that, will bend those pins and basically render the motherboard destroyed. And when you go to turn it in for a warranty repair, they will look at that. And if they see that the pins were bent, you may have a problem collecting on that warranty. So now, with the load plate lifted up, we are ready to actually drop the processor in. Now, if you take a look at the processor, you'll see that it has notches on either side, and they're offset, to one end. And those notches have to align with special indents on the side of the socket. So basically, take a look at the socket and look at where those indents are, and drop the processor into place. There you go. Now the processor is set into the socket. However, there's still no tension on it. In order to have it fully installed, we need to drop the load plate on top of it and then kind of press it down a little bit and use this load lever to put all of the tension on it, and then put the lever underneath the retaining tab on the side. So at this point, the processor is now installed in the socket. The load plate is putting pressure onto the top of the processor so that all of the lands on the bottom are in contact with all of the pins in the socket. So it's as you can see, it's fairly simple and straightforward to install a processor. Now, if the processor is of the type that uses pins, it works very much the same way. You don't have a load plate, but you do have a lever which releases tension on what's called a zero insertion force socket. Then you drop the processor into the socket, observing the correct orientation, and then you basically close the zero insertion force lever, which then applies pressure to all of the individual pins. So whether it's a pin processor or a land grid array processor like this one, the installation is very similar. Okay, now, with the processor installed, we have to deal with the heatsink. Now let's talk about heatsinks for a second. I have here the heatsink that came with this processor. Now, heatsinks are made out of usually either two materials, sometimes both. They're made out of either copper or aluminum, and this particular heatsink has both. It has a core of copper surrounded by fins of aluminum. Now, why the different materials? Well, copper is one of the best thermal conducting metals that there is. Silver is a little bit better than copper. It's like 5% better as a thermal conductor, but it costs 80 times more. So we don't usually see solid silver heat sinks. However, a solid copper heat sink would really be the best design. It would conduct the second most heat next to silver away from the processor. So why don't we see heat sinks that are all copper? Well, the problem is copper is expensive. It's a lot more expensive than aluminum. It has twice the thermal conductivity of aluminum, but it also costs from 3 to 9 times more, depending upon whether you're going by weight or volume. So the compromise is that many heat sink manufacturers, what they'll do is they'll have a copper core, like you see on this one, and then surround it with fins made out of aluminum. Some, depending upon the performance nature of the heatsink, some heatsinks might be all aluminum, or some might be all copper. In any case, that's the different types of metals that you'll see. Now, in addition to talking about that, we need to talk about what's called the thermal interface material. That's the material that basically has to go between the processor and the heatsink. Now, the thermal interface material is basically a grease or a wax type substance that make sure that that there's no little tiny air gaps, that the maximum amount of heat is transferred from the top of the processor to the heatsink. If you don't use the thermal interface material, you're compromising the performance of the heatsink dramatically. And what that'll cause is that in many cases the processor will overheat or not be able to run at its full speed, because modern processors don't actually overheat to the point of destruction or stopping. What they'll do is throttle themselves down. So you'll end up with a system that for some reason doesn't seem to be running as fast as it should be. The real reason is, you don't have a good bond between the heatsink and the top of the processor. Now, thermal interface materials come in two main types. One is called a phase change material. The other is called a grease. Now, phase change material is a wax type substance that is a solid at room temperature and which then melts at somewhere over 113 degrees. So when the processor warms up, this stuff will melt and then liquefy and perform as it should. When companies like Intel and AMD deliver their boxed processors with the factory included heatsink, what they will do to minimize, or to make the installation as easy as possible, they will pre-apply a phase change type thermal interface material to the bottom of the heatsink. I'm going to show you an example on the screen right now of what that looks like. As you can see in this example, there's like 3 bands of material, and it's a waxy type material. You don't want to touch it. You want to keep it protected until you actually install it, because you can damage it, with your finger. Once the processor is first powered up, that stuff will melt, and then it will ooze to where it covers the entire top of the processor. Now, with any thermal interface material, once you remove the heatsink, you have to take that thermal interface material and discard it. It has to be cleaned off. Usually you can clean it off with a paper towel. You can also, sometimes you need alcohol to help dissolve all of it. You want to clean it off the top of the processor and the bottom of the heatsink. Every time you reinstall a heatsink, you need to use new thermal interface material. And since, as an individual, I can't really get the phase change stuff, the only way you get that is pre-applied, we have to use what's called a thermal grease. Now, thermal grease usually comes in packages like this. Here's a package of what's called Arctic Silver, and this is enough for probably hundreds of applications. I couldn't, there's enough in here to install 100 heatsinks on 100 processors. Sometimes when you buy a heatsink, it will include a small amount of thermal interface material like this, a small little, this is good for, maybe 1 or 2 applications. They just give you enough that you can get it properly installed at least one time. Now, this stuff is a grease. Now, what are the differences between that phase change material and the grease? Well, the grease has a couple of problems that the phase change material doesn't have. One is called pump out, and the other is called dry out. Now, pump out refers to the fact that as the as the heatsink sits on top of the processor, there is slight movement due to just different thermal coefficients of expansion, contraction, vibration, and eventually this movement kind of pushes the grease out. It kind of extrudes, it oozes out from between. So eventually, there's not an insufficient amount in there. The other thing that happens is it dries out. The grease has like a silicone, usually oil, to suspend the thermal material, and eventually it can dry out. So those are some of the drawbacks of the grease, and that's why the manufacturers like to use the phase change material. Now, I've had people buy, processors that come with heatsinks and scrape the phase change material off, never even using it, thinking that the grease is better. Either one, performs pretty much the same thermally. In fact, I've seen numerous tests of, hundreds of different types of thermal interface material, and rarely see more than a 1 degree difference in the actual operating temperature of the processor, depending upon the different materials. It's just, it doesn't really matter. So people always ask me, what kind do you recommend? Do you recommend the Arctic Silver or, something else? I recommend whatever you have. Just use whatever you have. As long as it's properly applied, it's going to work properly. So, in this case, we've removed, I had already installed this heatsink once and had removed it. So now I need to reapply the thermal interface material to this processor. Now, in order to do that, I usually like to use a plastic or rubber glove in order to smooth the material out. So I'm going to put that on here. And I'm going to use this Arctic Silver material. And you're basically just going to put a blob of the stuff on the top of the processor. Not a whole lot, actually. Okay, now, once that's there, you want to use the glove and basically kind of smooth it out to where it covers most of the top of this heat spreader. Now, even if you don't get all of it, the entire heat spreader covered completely, it will ooze, around, especially as the force of the heatsink is applied on top of it. So, okay. As you can see, I've got this stuff pretty well smeared over the top of the heat spreader. Now I can take the glove off. Don't need that anymore. And we can actually install the heatsink on top of the processor. Now, Intel heat sinks are noted by these 4 push pin retainers, and they have arrows on them that what's kind of funny is that when you install the heat sink, the arrows have to be turned, or the knobs, the top of these retainers have to be turned the opposite way of the arrow. So I'm making sure that all those are turned in the right direction. It's a common mistake that people look at that and see the arrow and think, oh, well, I have to turn it. That's actually for the removal of the heat sink. So make sure these are all with the proper orientation. And then what we can do is set the heat sink down on top of the processor, aligning these 4 push pins with the holes in the motherboard. Make sure they're all there. And then what we have to do is we're going to have to use a lot of force to push these pins down and lock them in place. Now that's another reason why having the board out of the system in a tray like this is a big advantage, because I can get my hands in there easier to apply the right amount of pressure. I like to do it on opposite corners. You basically push down until you hear them click into place, and then I'll do these 2 corners until they lock into place. And then take a look around, make sure that all of them look the same and that they're all fully seated. These are. Now once the heatsink is installed, you want to connect the fan, which is right here, and plug that into the CPU fan connector. Most modern processor heatsinks use what's called a 4-wire pulse width modulated fan. And what that 4th wire does is basically it enables an infinitely variable fan speed control. So when you first turn it on, it'll start out slow, it'll spin very slowly. As the processor heats up or warms up, the fan will run faster and faster in order to maintain the proper cooling. So, as you can see, installing the processor and heatsink in this type of a motherboard is not that difficult. That's ready to go. Now, to finish this up, let's install the memory, the RAM in this system. Now, the memory is going to be installed in these sockets here. Now, this uses a triple channel memory, so we were installing memory modules in groups of 3. And you can see 2 different sets of 3 sockets here. There are there's 3 white sockets and 3 blue ones. Now, according to the manual for this motherboard, it says we need to use the white sockets first. That's the first channel, and then first set or bank, and then the blue sockets are the second. So since we only have 3 modules, we're going to install them in the white sockets. So I'm going to move these retaining tabs out to the side on the white sockets. Then I can get my memory module and make sure that the notch on the module is lined up with the notch in the socket. And then I can basically set it into place and then apply sufficient pressure straight down until it locks into place. Make sure these tabs are fully engaged and it's all the way seated down. Then I can go on to the next one, same thing. Press down until it's firmly seated. Make sure these tabs are locked into place. And then finally the last one. And again, make sure they're all in place. You might want to take a closer look, make sure that all the modules do seem to be fully seated. We don't want them on an angle at all. If a module is partially installed and you power the system on, you risk burning the modules and damaging the motherboard as well. So at this point now, I have the processor and heatsink installed. I have the memory installed. I can now take the motherboard out of this tray and then install the fully loaded motherboard into the system. Now I'm ready to install the motherboard in the case. Now, in order to do that, first thing I need to do is make sure that I've got all the proper screw hole positions. What we have here is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 standoffs or mounts in the case that match the 9 holes on the motherboard. Now in some cases you'll find motherboards that require screws in different positions. You'll notice some extra drilled holes here, and usually the little bag of screws that come with the motherboard will provide extra standoffs like this one that you can screw in if you need the support in those areas. Now make sure that they match the holes in the motherboard. So in this case, the existing 9 holes are exactly what's correct for this board. So with that taken care of, the other thing I need to attend to is the I/O plate that's mounted on the back here. This is the I/O shield, they call it. Now the case comes with one here, but this one doesn't fit your motherboard, so you're going to basically have to break this out, and it's usually just there we go, piece of thin metal. Take that out, and then you need the one that comes with your motherboard. And what you're going to need to do is to press that into place inside the case. So secure it in the proper position, and okay, I've got a little bit of a problem here. This fan bracket is actually in my way. I'm going to have to take it out. Okay, with the fan bracket out of the way, I can now successfully mount the I/O shield. It basically just sets in the opening here, then you kind of push it into place until it kind of clicks in. So it should kind of snap into place. Sometimes it can be a little tricky, but let's see if we can't get this one in here. Okay, now I've got the I/O shield successfully mounted in the case, and I'm ready to actually install the motherboard. So to do this best, it's easiest if you lay the case down and basically kind of load the motherboard in from the front to the back. So I'm going to turn it around so that as I slide it in, it presses up against the I/O shield and all the ports become available. Now, one thing you have to be careful with, there's some little grounding tabs that kind of stick out on these I/O shields, and they can get bent up, and I've seen them actually get like stuck in or inserted into some of the ports here. So you want to make sure that doesn't happen as this presses up here. So I'm going to set this down, kind of push it back, make sure all these connectors are lining up. Oh, I've got a little bit of a problem right there. Okay, this particular I/O shield has holes for two different network cards. I need to bend this one up so that the network card port on this particular board is visible. Okay, now I can try that again. This is lining up. Okay, all the ports seem to be lining up. What I can do now is start putting the first of the screws in. Now I assembled 9 screws from the little hardware bag that came with the case. And one thing I wanted to point out here, notice I'm using a magnetized screwdriver. I think it's a requirement when working on PCs. In fact, Intel recommends it as a way to prevent damage to motherboards, because what will happen is it keeps the screw in the tip of the driver and prevents it from walking out. So a lot of people say you shouldn't use magnetic tools around a computer, and I beg to differ. Magnetic tools make working on a computer, or I consider it a necessity when working on a computer. Doesn't cause any harm to any of the circuitry, so it's not a problem. So now we're going to install all of the screws. Sometimes I like to just start them manually and then use the electric screwdriver to tighten them. I like to get them all just started. A lot easier to get to everything when the power supply and everything is removed. Okay, now if you're a little uncomfortable with the electric, don't hesitate to just use a manual screwdriver. The last thing you want to do is have the screwdriver walk out of the screw and go tracking across the motherboard cutting traces. So at this point, we now have our motherboard installed in the case. And you want to double check here on the back to make sure all the ports are free and visible, and none of those little grounding tabs have sort of jammed their way into any of the ports or anything like that. And it all looks pretty good. So at this point, our motherboard, processor, and memory are installed. In this series of segments, we're going to build a PC from scratch. Now, I've started by laying out all the components I'm going to use, and let's go over a few tips and tricks before we get started. Now, number one, to do things by the book, you should wear an ESD, electrostatic discharge protective wrist strap. So I'm putting that on here, and I have it connected from my wrist to an anti-static mat onto which I've laid out the motherboard, video card, processor, and RAM. And then another jumper goes from the mat to the case, where I've got it clipped to an unpainted area on the chassis. Now, while I actually build this system in the interest of having things, be viewable better by the camera and in the interest of saving time, I may not use it. But take it from me, it's a good idea to use these components if you're building your own system. These components are these parts are expensive, and you don't want to risk damaging any of them due to a static discharge. Now, if you don't have the wrist strap and such, what you need to do is touch the frame of the case every time you go in to handle something. And if you're going to grab the motherboard or a circuit board that's out of the PC, touch the one of the grounded metal areas, like on the connector shells, or in the case of the card, touch the metal bracket before you pick up the card. And it's best not to touch any of the components. Processors will come with a protective covering the pins or leads, and you want to keep that on until you are ready to install it. So I've got all my parts laid out, everything's ready. A couple of tools that I'm going to need. I basically do almost all of my work with an electric screwdriver. Some people prefer to use a manual screwdriver. That's fine. It just may take a little bit longer. With an electric, you do have to be careful. In some cases, you don't want the bit jumping out of the screw head and, trekking across the motherboard, causing damage and things like that. So that's one thing. Also, if your heatsink doesn't have pre-applied thermal interface material, you're going to need something like this, which is some thermal grease, in order to put on top of the processor to better transmit heat to the heatsink. So other than that, I may need a few other tools here and there, some tweezers to get at jumpers and things like that. But that's it. So let's get started. In this segment, I want to talk about chassis, cooling, and power supply. Now, by chassis, I mean the case that the PC is built in. Now, I've built a lot of PCs, and one of the most difficult decisions I always have when it comes to building a system is selecting the right case. There are so many to choose from, and not a single one has all of the features I look for. So it's always a trade-off. I'm always balancing certain parameters over others to decide what is the best case. Now, this is one that I've actually been using for the last year or two in most of my builds. This is an Enermax Vostok case. And while it's not perfect, it has a lot of good features. But we'll take a look at what's good and bad about cases in general. Now, let's discuss, first of all, cooling, what I think is proper cooling in a case. To have proper cooling, you need more airflow flowing out of the chassis than flows in. So one of the things I look for on the back of a case is a large rear exhaust fan. Now, cooling fans come in 3 different sizes as far as desktop PC cases are concerned. 3 main sizes. We have a 120 millimeter, we have a 92 millimeter, and we have an 80 millimeter. Now, years ago, cases used to come with the 80 millimeter fan in the back, single 80 millimeter fan. That proved to be, not enough. Plus, the fact that smaller fans tend to make more noise. So, in the interest of having both more airflow and quieter PCs, we generally went to 92 millimeter fans or even 120 millimeter fans in the back. I generally won't buy a case unless it has either a 120 or a 92 millimeter rear chassis fan, preferably the 120. Now, this is an example of the 120 millimeter fan, and that's what this case came with. And one nice feature about this case is that the fan clips into a bracket that's installed into the case. So the brackets, once the bracket is screwed in, you can easily snap the fan in and out. Being able to take it out quickly and easily makes loading the motherboard a little bit easier. If the fan ever does fail, you can snap in a replacement, very easily. It just literally snaps onto these brackets. So that's one thing to look for. 120 millimeter fan in the back blowing air out. Now, power supplies also have fans, and the power supply will also exhaust air out the back. So now we've essentially got two fans, pulling air from inside the system and exhausting it out the back. Now, where does that air come from? It has to get into the system somewhere. Well, almost all chassis have a vent on the front, and usually it's going to be down below. There's an opening in the front of the front panel, down at the bottom here, where air will go in, and then if I turn this case around, you can actually see where it will flow in through the front of the case here. Now, many chassis like this one not only have just openings there, but there's actually a mount for a secondary fan. Now, one of the features I like about this case is that I can hold a lot of hard drives. 1, 2, 3, 4 hard drives right here, and I can even mount additional hard drives in these 3.5-inch floppy drive bays. So I could actually have a stack of 6 hard drives here if I want. That's a lot of hard drives. And hard drives can, especially when you've got several of them grouped together like this, they can generate a lot of heat. Generally, if I'm installing more than 3 hard drives, if I'm putting 4 or more hard drives in the front of a case like this, I'll want to add the optional front cooling fan. And what that'll do is pull more air in across the drives. So what will happen is the fan on the back will be mounted so that it blows air out the back, but the fan on the front will be mounted so it blows air in. Now, the key, what you want to do is make sure you have a balance here. You need more air going out than in. So if I have a 120 millimeter fan on the back blowing air out, I generally like to have a 92 millimeter fan pulling air in on the front. Now, why do you want more air going out than in? Well, because there are other vents on a case. For example, if I show you the side panel for this case, you can see that it has several vents. There's a vent here. This is a vent for the video card. In order to better cool the video card, Intel and other manufacturers came up with the idea of having a vent here so that air can be drawn in. Now, if you have more air blowing into the case than coming out, there's not going to be air drawn in through this vent. It's going to be hot air coming out of it, and that's not what you want. Also, here's a vent for the processor. This is the mark of what's called a thermally advantaged chassis. That's Intel's fancy term for having a processor vent. And what you will find is a duct that's adjustable. You can actually move this in and out in order to get as close or close enough to the processor heatsink, the processor fan, so that it will pull air from the outside. See, the idea is that the air inside the case is heated up. So in order to better cool the processor, we want to draw air directly from the outside to cool the processor. So again, that's why we want more air generally coming out than being blown in, because we want to create a suction. We want to create a vacuum so that air is being taken in through the various vents on the system. So again, what we can do in this, if I'm going to mount 4 or more hard drives, I'll usually take a 92 millimeter fan and mount it up in the front here so that it'll adequately cool all of those hard drives. Okay, you can actually go crazy with fans, and that's something that I don't think is necessary. I rarely build a PC, even a high-performance PC, with more than 2 fans, one in the back, one in the front. Of course, you can consider the fan that's on the heatsink for the processor. That's another fan, and there's one in the power supply. So all told, there are 4 fans in the system, but I'm talking just about the chassis fans. Okay, so the general airflow in the system is going to be from the front, across here, up and out the back, and we're going to be able to cover the motherboard, the processor, video card, through all of the other vents in the system. So from a cooling perspective, this case is very well designed. All right, what other things do we look for in a case? Well, one nice thing to have in a case, which this case doesn't have, is what's called a motherboard tray. That's a removable tray like this, which you would mount the motherboard on, and then insert the mounted motherboard into the case. Having a tray like this makes it a little bit easier to install the processor and heatsink and memory, because you do all that with the motherboard out of the system. If you don't have a motherboard tray like this, then technically you have to put the motherboard in the system before you install the processor and memory. And it can be a little bit difficult because you've got this, the side walls and the bottom and the top, and you can't really see as well. Well, as a compromise, what I've done is I've saved motherboard trays like this one. I've saved from another case that I had discarded years ago. And so what I'll do is I'll temporarily mount the motherboard on this tray, install the processor, memory, heat sink and such, and then I can take it off of the tray and install it in the case, and that makes things a whole lot easier. So that's one little tip there for you. Because unfortunately, finding a case with every single feature you're going to want, like a motherboard tray, is not going to be always possible. All right, what else do we look for? All right, well, this is something that may seem like a good thing, but actually ends up not being that good, and that is these quick-release drive mounting mechanisms. The idea here is that you would be able to, like, literally turn this, take this off, slide a hard drive in, put this in, and lock it into place that easily. It's a no-tools hard drive mount. Here we have two no-tools mounts for optical drives. You can just slide the drive in and quickly latch them in with these plastic attachments. Well, the problem is they don't really mount very securely. They allow the drive to move a little bit, and you end up getting rattles and noise. And without the secure mounting, without screws going in through the case, through on either side, you lose a bit of rigidity too. So every time I used to like these kind of things, but anymore I take them out and discard them, and I mount all of the drives with screws. It does take a little bit more time, but I think you end up with a more securely mounted set of drives. The cooling is better because they're more directly attached to the metal of the case, and it just seems to work out better. Now here's another feature which some may find as a drawback, but I actually think is a bonus. This case is made of very thin metal. It's very lightweight. Now, some people think, oh, I want a heavy case. I used to be in that of that mentality myself. I wanted the thickest steel, heaviest case possible. Well, after carrying enough computers around for years, I've decided that, a lighter case is better. And that's another reason I like to screw all the drives in. With all of the drives screwed in, the whole rigidity of the case is greatly enhanced. So what was a lightweight case becomes a strong lightweight case. So I'm actually a big fan of the thinner, lighter cases. Yeah, if you drop it, it's going to bend or dent, but you really shouldn't be dropping it. So what else do we look for in a case? Well, this is one of my biggest problems with cases in general, and I think it gives especially novice builders the most trouble, and that is the front panel connections. You know what I'm talking about. I took this off of another case. Most cases have, you have a reset button and a power switch that are mounted on the front, plus you have a hard drive LED and a power LED. How do those things get connected to the motherboard? Well, if you've ever built a PC, I'm sure you've seen these, you have these 4 different connectors. They're 4 little 2-pin connectors. And some of them are polarity sensitive. The ones for the LEDs have to be in the right polarity or the LED won't light up properly. And it's easy to miss pins. Plugging these in is the bane of PC builders everywhere. It causes no end of trouble. You can't see what you're doing, because you have to do this with the motherboard already installed. You can't do it with the motherboard out of the system. Now, if you've ever seen cases from companies like Dell, Gateway, or, in other words, pre-built, mass market PCs, you'll note that they almost always have cases with front panel connections that have a single connector. This is one keyed connector that makes all of those connections at the same time. Now, believe it or not, Intel created a standard for this front panel connector more than 10 years ago. In fact, I think it's like 15 years ago now. And almost all any motherboard that I would ever buy anyway, follows this standard and has this standard type of connector. So the need for these individual pins it's ridiculous. So what I do, in fact, what I did with this case did not come with this connector on it. It came with an arrangement just like this. What I do is I take these individual 2-pin terminals off. I purchase a single 10-pin connector like this. You can buy this from a company called FrontX. That's frontx.com. They sell these individually. You can also buy them in bulk from any electronic supply house. And I simply insert the pins. I don't even have to cut the wires or do anything with the terminals. These are the same terminals that go into this connector, and I simply insert them in this connector in the right sequence and right order, and you find the documentation for that in my book. And then, after just a few minutes of work with this, from that point on, I now have a single front panel connector on my case. So anytime I remove the motherboard or have to plug it back in, it's one single keyed connector, very easy, nothing to mess up. That is a tremendous tip. Also, I look for, this one has a front panel USB connection right here. Make sure that's a single connector like this. In many cases, you'll find those are multiple connectors as well, which is totally unnecessary because that is a standard. And then likewise, here's the audio connection for the front panel. This case has, like many do, speaker or headphone and microphone jack and USB on the front. And motherboards have connections for those. They're an industry standard, so you want a single connector to plug in, not a bunch of little connectors like this. That's a nightmare. All right, so what else do we look for in a case? Well, cases, generally when you buy a case like this case, I believe costs like $50 or $60. The power supply that comes with a case like this, if it does come with a power supply, is usually not necessarily the best type of power supply. For example, I'll note a couple problems with this one. This power supply that came with this case has literally one SATA serial ATA drive power connector. Now I plan on installing 4 hard drives in this case, and I could fit 6. I'm not going to be able to power 4 or 6 hard drives with a single connector like this. Now you can get adapters. Here, for example, I purchased a what's called a Molex 2 serial ATA power adapter, and I can plug that in, and now I have another serial ATA power connector. I guess I could get a couple more and use these, but we simply don't have enough drive connectors, period. There's only 2 more, and I have 4 hard drives plus an optical drive that's going in here. So bottom line, this power supply is inadequate, and I'm probably going to need to replace it before I build a system. So that's one thing to consider. Anytime I buy a case, they generally tend to come with cheap power supplies. I consider that to be a throwaway. Maybe I'll keep it as a spare, be able to use it in another system someday. But I'll probably replace it with something else. Now, when you go to replacement power supplies, you need to make sure that the power supply you're purchasing has the proper connectors for not only the drives you want, like for example, you need, if you're going to install 5 serial ATA drives, you're going to need 5 serial ATA power connectors. You also need to make sure that it has the right main connector for the motherboard. Now this one has a 24-pin connector, which is what most motherboards use today. So that's a good thing. And this one also has the 4-pin CPU power connector. Now the 4-pin CPU power connector is what most motherboards use. But it just so happens the motherboard I'm going to put in this system has an 8-pin CPU power connector. Now you can actually plug the 4-pin into the 8-pin, but if you use a high enough powered processor, it's not going to have adequate power. So what you'll want is to find a power supply like this one. This is a bigger, heavier duty power supply I have on top here. And this one has an 8-pin motherboard CPU power connector. You can see the difference here, 8 pins versus 4. Now you can get adapters to turn the 4-pin into the 8-pin, but that doesn't provide more power. So the idea is that if you need a bunch of adapters to make your power supply work with what you have, you probably don't have an adequate power supply to begin with. So while an adapter here and there is okay, if you start using adapters for everything, it just means you don't have an adequate power supply. Now another thing to look for is many video cards require their own power, and those come in the form of a 6-pin power connector. So this has what is called 2 PCI Express video power connectors, so I can run 2 high-powered video cards. If I was going to do an SLI with 2 video cards running simultaneously, this would be able to power that. So in fact, video cards can be one of the most power-hungry devices in the system. There are some video cards that consume more power than entire motherboards and processors do. So keep that in mind if you need a higher output power supply. Now, I know power supplies are rated in watts, and more watts is better in general. However, not all ratings are the same. Not all manufacturers are honest about their ratings. One of my favorite power supply manufacturers is PC Power and Cooling, and their ratings are rock solid. So when they say it's a 500-watt power supply, that's exactly what you get. I've seen 500-watt power supplies from cheap manufacturers, which I would take a 250-watt power supply over that so-called 500. They're so cheaply made. So we want to make sure we have, as I said, the adequate power to power the motherboard, video card, all of the drives in the system. Now, one point about power supplies. The ATX standard calls for a power supply that's 140 millimeters deep. But there is an auxiliary to that standard that allows the power supply to go as deep as 180 or more millimeters. And this is an example of the deepest type of power supply. These are called EPS power supplies. And as you can see, this power supply would actually fit in this case. I could take this out. The screw holes and everything are identical. 4 screws hold this in. The same 4 screws would hold this one in. The only issue is that I need to make sure that the case is long enough so that the optical drive will fit in the front. And in this case, as in most of them, it actually will. Most of the optical drives are shorter these days anyway, so there's adequate room between the end of the power supply and the optical drive. So that's an issue. If you want to use a really high output, this happens to be a kilowatt, 1,000 watt power supply, probably overkill for most things. But if you have one of these deeper, so-called EPS power supplies, you'll want to make sure that you have room. So that's something to consider there. Now, if you are using a new power supply with an old motherboard, in some cases there are adapters that can handle that. These power supplies typically have 24-pin connectors. As you can see, this type of adapter will adapt it to a 20-pin, which is what the old motherboards used. Now, in many cases, you can actually insert the 24-pin connector into the 20-pin connector on the older motherboard and have 4 pins hang off. They will literally hang out in space and not cause any problems. But in some cases, there are components that interfere. So that's something that you may have to deal with. So with all of these things in mind, we've taken a look at cooling, tips on cooling. We've made sure we've got the right features in our case, and we want to make sure we have adequate power to power the motherboard and the video cards and hard disk drives and everything else we're going to put in the system. In this segment, I want to discuss hard disk drives. Now, in looking at modern hard disk drives for desktop systems, we basically have 2 main choices today, and most of the time it's not really even much of a choice. In front of me, I have 2 3.5-inch hard disks. One is of the older parallel ATA configuration, and this one here is of the newer serial ATA configuration. Now, virtually all systems you'd be buying or building today would use serial ATA drives, but I just want to point out a couple of differences and one tip also about the newer serial ATA drives. As you can see with the older parallel drive, the reason it was parallel is because it had a multi-pin connection. It had 16 bits actually of data going down this cable simultaneously, and that was a parallel transfer. On the newer serial ATA, we have only a 7-pin cable, and literally only 1 bit at a time is sent down the wire. So obviously with the serial ATA, you can see that the cable is much smaller and easier to handle. It's not this wide ribbon cable. But also there's a couple of other differences. One is the power connector is different. Serial ATA drives generally use a different power connector. Now here's one potential problem. Some of the early serial ATA drives actually had both types of power connectors. That is, they had the old Molex type, which is shown here, as well as the new serial ATA. You'd actually see both of them on the back of the drive. If you plug both types of power connectors in, you could literally destroy the drive. So there were warnings about that, and the manufacturers have quickly stopped including the second power connector. I kind of liked it when they did, because oftentimes I was running into power supplies that didn't have the sufficient number of serial ATA power connectors to power all the drives I wanted to put in there. And when the drives had both, no problem. I could use the older style power connector to provide power to the drive. The important thing to note was you just can't plug 2 power connectors into one drive. That does not work. In fact, it can cause damage. So that's just a warning there. Now, the other problem with the older parallel ATA drives is that you always had to deal with a jumper, or at least almost always. Now, on newer setups, they used a jumper position called cable select, and that means that let the cable decide whether the drive was master or slave. Prior to that, you had to specifically jumper the drive as master or slave. Now, with it set in cable select, when you would plug it into the black connector, like I have here, that would be master, and when you plugged it into the gray connector, shown here, that would be slave. The blue connector on the cable always went to the motherboard. So we had the motherboard connector, slave connector, and master connector. And if you had a cable with the connectors color-coded like that, that's a cable select cable. And then you would jumper the drive in the cable select position. So if you encounter systems, older systems, you're working on them, you need to, install new drives or, repair the system and install a replacement drive, you'll need to be concerned about that. Now, serial ATA drives, they don't have any jumpers, right? It's just a one, connection. There's no master or slave. Well, that's not exactly true. You see, there are two variations of serial ATA drives available. Those that did the original 1.5 gigabit per second speed, and those that do the newer 3 gigabit per second speed. Sometimes those are called SATA 2 drives, which is actually inappropriate terminology. They are technically SATA 3 gigabit per second drives. This is a 3 gigabit per second drive. However, what was discovered was that sometimes if you had an older motherboard that had a 1.5 gigabit connection and you plugged a 3 gigabit drive into it, they wouldn't talk. The drive would not be seen or it wouldn't work properly. So almost all of the serial ATA 3 gigabit per second drive manufacturers are including a limiting jumper on the drive that will knock the drive down to 1.5 mode. In other words, cut the drive speed in half. And guess what? Virtually all the drives I've seen lately ship with that jumper enabled. So I just bought 6, in fact, of these serial ATA drives. Every single one of them had the limiting jumper in place to knock it down to half the speed. That jumper is, by the way, positioned right here. It's a little tiny gray jumper on this drive. I need to get a tweezers out and take that jumper out, because the motherboard I'm going to be connecting this to will support the 3 gigabit per second rate, and why would I want the drive running at half speed? Most people don't even think about this. They don't know about it. They just install the drive, think everything's okay. So that's something to be concerned about. Now, if you do use a newer drive in an older motherboard and it's not working, then you may need that limiting mode set. So that's something to consider. Now, since we're almost always using serial ATA drives today, there are actually 2 different variations of drives that I wanted to talk about. There's your standard drive, and then there are what are called enterprise or RAID class drives. That's the only kind of drive I buy today. Well, in fact, I normally do install drives in arrays in many of the systems that I build, but even if I'm dealing with an individual drive, I always buy the RAID or enterprise class drive. Why? They are more expensive. They can be 10 to sometimes 20 or 30% more money for the same capacity drive. They're simply more reliable. They have better error correction circuitry built in. They have longer warranties. They're designed to be more durable, more rugged, and they have special error control protocols such that they won't time out in a RAID array. So if you are using drives in an array, you absolutely need the RAID ready, so-called RAID ready enterprise class drives. But even if you're not, I highly recommend them. I don't know what's going on. I mean, I had hard drives lasting years with no problem for many years, but over the last 5 years, I've seen just a large number of drive failures. I think drives have become such a commodity, the prices have become so low that we're just seeing, the manufacturing processes are a little bit less, well, they're less expensive. So to fight that, I buy enterprise class drives. Now, this is especially important if you're dealing with external drives. Now, a lot of people will go to the store and buy an external, USB or FireWire or even eSATA drive. And what they're getting is a drive enclosure, like this. And in that enclosure comes a hard drive. Well, you're never going to get a RAID class or enterprise class highly reliable drive in a pre-built enclosure. So what I recommend is buy your own enclosure. This one costs $30. And then I buy my own, RAID class, enterprise class drive, and I simply build my own. It doesn't cost me, in fact, it generally costs me less than the pre-assembled store-bought enclosure with the drive already installed. Now, another thing you can take advantage of with the serial ATA drives is eSATA. That's E for external serial ATA. Now, you can, in fact, many motherboards will come with this. This is a SATA to eSATA bracket and cable assembly. So this connector here plugs into the SATA connector on the motherboard, and then it presents an eSATA connector on the back of the PC. Now, eSATA connectors are different from SATA connectors. I mean, this connector will not plug in here. This connector is designed for internal use only. This connector is designed for external use. So if I have an eSATA capable drive enclosure like this one, what I will want is an eSATA cable like this one here, which I can then plug into this connector. It provides a reliable connection that's designed for external use, and then this will plug into the drive. The advantage of eSATA, you can have that same high-speed connection that you have internally with an external drive. This is 2, 3, or more times faster than USB. So if you use external drives a lot for backup, you deal with large files, and you want the fastest transfer rate, go eSATA. Now, here's one disappointing thing. Virtually all of the external enclosures that support eSATA only do so at the 1.5 gigabit per second rate. So even if you have a 3 gigabit per second drive like this one, it's only going to work at 1.5 gigabits per second via eSATA. Now here's where knowing about that jumper may come in handy, because if you build it and it doesn't work, you may have to install the limiting jumper depending upon what type of circuit board is in the particular enclosure that you're using. Now, if you deal with a lot of external drives, you want multiple eSATA, you can actually get brackets like this one here that have 2 eSATA ports on them. So that's something to consider. And that way I could run multiple enclosures and copy from drive to drive and things like that at virtually the same speed as having the drives internally mounted in the system. So I hope these tips will help you, build, both buy more reliable drives, connect them up properly, make sure that they work, and even if necessary, build yourself your own more reliable external enclosure. In this segment, we're going to talk about motherboards and take a detailed tour of a modern motherboard in a system. Now, when you're buying or building a system, the motherboard is the main platform into which the processor is plugged into, the memory, all your expansion cards, etc. So in many cases, it's really the most important part of the system. I know a lot of people think of the processor as the most important, but the motherboard is what the processor itself plugs into. Now, normally when you're putting together a system, buying or building, you're going to decide, oh, I want this certain type of processor. Then that gives you a range of chipsets to consider. See, the main circuitry on the motherboard is what we call the chipset. Now, modern motherboard chipsets normally consist of 2 chips, what we call the north bridge and south bridge. I have a diagram here showing a typical motherboard block diagram, and the north bridge and the south bridge are these components here. The processor would be in the socket represented by this top portion of the diagram. So when, let's say you want to build a system with a Core i-Series processor from Intel. Well, you'll have to look at what chipsets support the specific processors that you wish to select. Then you need to examine only motherboards with those chipsets. Let's say you want to build an AMD Phenom 2-based system. Again, you need to find out what chipsets support that processor, and then you can then narrow down the choice of specific motherboards from the motherboards that support that processor. Now, one of the other big choices to make in a motherboard is the form factor. The motherboard I have here right now is what we call a full-size ATX form factor. That is traditionally the most common. It's been in use since 1996, by far the most popular form factor. So if you're building a system with a full-size ATX motherboard, you have just hundreds, if not thousands, of different types of cases to choose from that will fit this board. Another choice you can make is what's called a micro ATX board. This is an example of a micro ATX board, and as you can see, it's basically a subset of the full-size ATX. I mean, it actually has a subset of the screw holes and of the dimensions. So if a case would fit this big board, it will automatically fit this smaller micro ATX board. Now, if you are building a system using a micro ATX board, you can buy a smaller case that will fit just the micro ATX board. Obviously, then the full-size board wouldn't fit in that. So that's another consideration. Generally, with the micro ATX motherboards, you have fewer slots, fewer expansion ports, and fewer features in most cases. However, there are some very fully featured, fully loaded, I should say, micro ATX boards. So now, let's take a look at this particular board in more detail. Now, as I said before, we have the socket that the processor plugs into. Then we have what's called the north bridge and the south bridge component that are part of the motherboard chipset. Let's see where those are physically on this board. Well, this motherboard is what we call an LGA 1366 socket, and that is right here. Now, the LGA 1366 stands for Land Grid Array 1366 pins. Now, land grid array means that the pins are actually in this socket. And that's why you'll notice this particular one still has a protective cover on it, which comes from the manufacturer, to prevent you from accidentally damaging any of the pins here. See, the little pins are sticking up from inside the socket, and if you were to touch them with your finger or snag them with a piece of cloth, you'd bend them and possibly render the motherboard inoperable. The processor itself doesn't have any of the pins. It just has lands. It just has basically gold spots that make contact with the pins when it's inserted. So you'll see these protective covers, and I recommend not removing this cover until you're ready to directly install the processor. The North Bridge component is right here in this case. Now, North Bridge chips in modern systems tend to run hot, so in most cases you will find some sort of a heat sink on them, as you see here. Now, this heat sink is a fairly advanced heat sink. It has what's called a heat pipe that helps distribute heat among voltage regulators here. This is voltage regulator circuitry for the processor. It basically provides power to the processor. Then we have the heat pipe connected again to the North Bridge, and then over here to the South Bridge. This is the South Bridge component, also under a heat sink in many modern motherboards. Now, in newer processor designs, what we found is that the both Intel and AMD in their most recent processors have moved the memory controller from the North Bridge, this is where it used to be, into the processor. So in this block diagram you can see I have memory modules that will be attached directly to the processor. The data flows between the processor and memory directly. It doesn't have to go through any other chips. And this particular design with the LGA 1366 uses 3-channel memory. So in other words, the processor can talk to 3 memory modules at a time. Now let's find that on the board here. Here we see the memory sockets, and we have 6 of them. So that means we have 2 separate sets of channels. We have 3 white sockets. That represents the first channel. So when I buy my first 3 memory modules, I'll plug them into those 3 white sockets. Then the 3 light blue sockets are the second channel. And when I buy, more modules, I'll plug them in there. Now, for maximum performance, being this supports 3-channel operation, you'll want to install memory modules in groups of 3 at a time. And all 3 should be the same capacity and the same speed, and ideally from the same manufacturer. So I recommend, in other words, buying them all at the same time. Now, you can run this in dual channel operation or even single channel. In other words, it's possible to run this motherboard with just 1 memory module in it, but you will lose some performance if you do that. Now, according to this diagram, you'll see that on the North Bridge component, we have a connection to the video card slots. These are PCI Express by 16 slots, and we can see those here, these 3 long slots, 2 blue ones and 1 sort of an orangish colored one. Why are they different colored? Well, the 2 blue ones support X16 operation. That means 16 lanes of connection, and both of those can be used at the same time. Now, the orange colored one here only supports 8-lane operation. So while you can use 3 video cards in this particular motherboard, the third one won't have the same performance. It'll have half the throughput of the other 2. So that's a limitation of the chipset. Now, what else do we have? Well, that's the only other connection from the North Bridge. So the North Bridge connects to the processor, it connects to the video, and then it connects to the South Bridge. Now, this North Bridge to processor connection is called QPI from Intel. That's Quick Path Interconnect. And that supports a very high-performance bandwidth of over 25 gigabyte per second transfer rate. So that's an extremely high-performance connection between this North Bridge and the processor. Now, let's look at the South Bridge. The South Bridge is a very much, how should I say, overworked or in-demand chip in a modern system. As you can see, look at all of the interconnects to the South Bridge. For example, in this we have the audio. And on this motherboard, we have audio chip, which is actually located right here. So this chip right here provides a connection to the audio jacks on the back where you can plug in speakers. This one happens to support 7.1 audio, and this happens to be a Realtek audio chip. What else do we have in here? We also have a gigabit Ethernet right here, represented by these two blocks here. The gigabit Ethernet chip is located right here, and that provides a connection to the Ethernet port on the back of the motherboard here. So there's the Ethernet chip. What else do we have? Well, a big portion of this is the interface to hard drives, and what we have is 6 serial ATA ports made possible by this particular Southbridge. This one happens to be called the Intel ICH-10R. That's I/O Controller Hub 10, R for RAID Edition. And we find those ports right here. There are 2, 4, 6 serial ATA ports that are connected to this South bridge. Now, on this motherboard, there happens to be 8 hard drive connectors. There's 2 more serial ATA ports here. Well, where did those come from? Well, that's from an auxiliary chip. See, some motherboards manufacturers will put accessory chips in there in addition to the chipset to provide additional functions. Kind of like, we mentioned the audio and the Ethernet. Well, this particular motherboard has a second serial ATA controller right here, which powers these 2 connections here. So we have additional connections for serial ATA. We can run up to 8 hard drives on this board. Okay, what else do we have? Well, if I look over at the diagram here, we also have a connection from the South bridge to up to 6 PCI Express by 1 connectors. Now, we don't have 6 PCI Express by 1 connectors on the board, but we have, here's a by 1 and a by 4 connector. Also, we have an interface to standard PCI. That's also built into that South bridge. These are for older, just standard PCI cards, not the PCI Express. Now, what else do we have in a board like this? Well, this board happens to have, a lot of additional features. It has, for example, over here, a built-in power switch and a reset switch. This board is kind of designed for overclockers, and when you're overclocking a system, you might get into a place where it locks up, and with the system open and having easy access to a power and reset button is something that they thought was desirable here. How about power connections? There are several power connections that are used in a modern motherboard. We have the main ATX connector here, which is a 24-pin connector. That's the main connection between the power supply and the motherboard. We also have an 8-pin CPU power connector here. This connector basically powers the voltage regulators, which then provide power to the processor. So those are the main connections between the motherboard and the power supply. Now, what else do we have on this board? Well, there's also fan connections. You'll see interspersed throughout this board several 3- and 4-wire fan connectors. This board has quite a few of them because it supports running not only the processor fan, but a rear case fan, a front case fan, and even other auxiliary fans. Typically, you'll find at least 2 or 3 fan connectors on most boards. Some high-performance boards like this one will have even more. This board has additional functions as well. Built into the South bridge are also USB ports, 12 in fact on this particular chip. So we have 8 USB on the back, and we have 2 USB headers here. These are designed for front panel USB ports. Each of these supports 2 more. Each of these headers supports 2 more ports. So you could have up to 4 front panel USB ports, and the cables for those would plug into these 2 headers here. We also have headers for 2 FireWire ports. And there's an additional FireWire port on the back of this board. And that's all supported by a Texas Instruments FireWire chip, which is located right here. So this provides 3 FireWire ports, 2 that you can optionally run to the front, 1 built in for the back. Finally, I wanted to mention here, over here is the connector for the front panel audio. In other words, if your case has jacks for a microphone and headphones and things on the front, you'll plug the cable from the case into this connector here. So that's an important connector to know about. So those are the main points that we see on this motherboard. You'll find that many modern motherboards have similar sets of connectors. And if you want to know exactly where things are located on your motherboard, I recommend you check the manual. I find that today, most motherboard manufacturers are really good about giving detailed diagrams showing where all the connectors are and what they're used for. In this segment, we're going to talk about memory types and technologies from the very first PC to the present. Now, having been involved with PCs since the very first one came out, I've seen memory change tremendously over the years, and I thought it'd be interesting to take a look at all the different types of memory that we've had available, and in some cases to see, the physical, how it appeared, what it cost, and that sort of thing. Now, going back to 1981, when the very first IBM PC came out, you didn't have very many choices when it came to buying memory for the system. And initially, you had this choice right here. This was a 64K memory card that was available from IBM, 64 kilobytes of memory. And at the time, this cost a whopping $540. See, back then, 9 16K chips, which is what it took to make up 16K, cost $100. And this actually has 36 chips on it. They're double stacked. There's two sets of chips from what you see here. So there's $400 in just these chips alone. And these chips ran 200 nanoseconds, which is about 5 megahertz in speed, which of course matched the speed of the PC at the time. Then, a year later, we had this card become available. This was a 64/256K card. This could hold 4 times the amount of memory as the first card here. And what we had was, this would have banks of 64K chips. We had 1, 2, 3, and then 4 banks of chips here. Normally, this card was sold with just 64K on it, and then you would manually add the rest of the chips. Back then, what we had to do was buy chips. They usually were sold in, in these little tube-like containers, and you would take the individual chips out of the container, like this. This is one of the memory chips. We'd load it into a memory insertion tool, like this, and then you would use this tool and put it over the socket, and then press down and push the chip into the socket using this tool. As you can imagine, it would take quite some time. I remember spending hours filling boards like this. I mean, look at the number of chips on this board. Think of how long that would take to make sure you got each one in. You had to have each one properly oriented, not miss any of the holes. And if you did, boy, you had all kinds of troubleshooting to go through. Well, okay, so we went from 1981 to 82. Then over here, I'm jumping up to 1985 with this card. This card came out after the IBM AT came out, and at the time, this card cost a whopping $475. Now, the good thing was that this card had up to 2 megabytes of memory on it. So we went from 64K to 256K to 2 megabytes. And for the 2 megabytes, of course, when you consider it was still about $500, the price per K had come down quite a bit. Now, after 1985, that was when we started to get away from memory cards. If you look at these cards, you'll note that they actually plugged into bus slots on the motherboard. Back then, the motherboards had very limited memory expansion, and when you wanted to add memory, you had to buy a memory card. The problem with these memory cards is that they were limited to the speed of the bus in the system. And oftentimes, even though the processor and other components on the motherboard were running faster and faster, the memory or the bus slots had to stay the same speed because cards had to be designed to work with them. So this was a very limiting in terms of performance. Well, in 1986, we had the first SIMs come out, and the first type were these 30-pin single inline memory modules. That's what SIM stands for. And the term single inline means that it's really one row of connectors here. You see a row of connectors on this side and a row of contacts on this side. Even though there are contacts on both sides, they are the same. They're redundant. Now, this particular 30-pin SIM holds 256K of memory. That's the same as this card here. So when you think about it, all of these chips are replaced by just 3 chips on this tiny little board. That was progress at the time. Well, from the 30-pin SIMs, we went to the 72-pin SIMs here. This is an example of a 72-pin SIM. This one happens to hold 8 megabytes. That's 4 times more than this entire card in just this little memory module. Now, back then, these modules ran at 5 megahertz for this. The board ran at 10, and these modules here ran up to 16 megahertz. That was the top speed available for memory at the time. Well, we had a breakthrough in memory when this type of module came out. This is known as a DIMM, and the type of memory that goes on this DIMM is called SDRAM, synchronous DRAM. And synchronous, the synchronous was important because that meant it ran in sync with the motherboard. This stuff was available at speeds up to 133 megahertz, which matched the speeds of the motherboards and the chipsets at the time. Now, the SDRAM was popular between 1998 and 2002, and it replaced these 72-pin SIMs here. So from 1998 to 2002, we had a lot of systems using this SDRAM. Now, starting in 2002, that was replaced by something called DDR SDRAM. The DDR stands for double data rate, and just as the name suggests, it ran twice as fast as the single data rate. So these modules were different. They were not interchangeable, different set of contacts. And these were also DIMMs, being that the memory contacts were on both sides, and they were different. So now we had twice as many contacts without having to have the module be much longer. So this is the DDR DIMM. After DDR, we had DDR2. Now DDR2 came out in 2005 and was popular all the way up until 2008, 2009. We're still using DDR2 today, but it's being replaced today by DDR3. Now, looking at the DDR2, that memory ran up to 1,066 megahertz. So that kept pace with the motherboards and chipsets at the time, up until we needed something faster. So what happened was from DDR2, we go to DDR3 memory, and that's the current state of the art that we're using today. DDR3 came out in 2008, but in late 2009 it started to become really popular, and that was when the price of the DDR3 equaled about the price of the DDR2. Now, when you look at prices of memory, it's pretty amazing. This DDR3 module that I have here costs only $40, and that's 2 gigabytes of RAM. 2 gigabytes for $40. I did some math, and putting that into 1981 terms, to buy that much memory in 1981 would cost over $8 million. That's how much the price of memory has come down. It's pretty amazing. So these days, if you're buying or building a PC, in most cases it's going to use DDR2 or DDR3 memory, with most likely the switchover is now happening very rapidly to DDR3. Now let's take a look at a little bit, how this technology works. We mentioned that the double data rate, ran at twice the data rate of the single data rate modules. Now DDR2 is not again is not like a quadruple data rate. What they did there was they added extra signal pins in order to improve integrity. So the speed, the clock could go higher. We could go up to 1,066 megahertz. With the DDR3, we're up to 1,600 megahertz with these. And in the future, they may even go faster. So most of the modern motherboards today will use DDR3. That's with the Core i series from Intel and the Phenom processors from AMD. Now, when you're installing memory, probably the biggest thing you have to look out for is plugging the memory in either backwards or not fully inserted into the slot. And I wanted to point out, here I have an example of a memory module that I took out of a system. And if you look here, I can see 2 pins where the gold has actually been literally burned off the module. That's because the person who installed these either didn't ensure that they were fully seated, fully inserted into the socket, or they plugged them in backwards. Now, to prevent plugging in backwards, you'll find keying in the form of a notch on the module, which must match the notch on the socket. Now, sometimes this can be confusing. For example, in the case of the DDR2 and the DDR3, they both have the same number of pins. They're both 240 pins. So, yet they're incompatible with each other. How do you make sure that the right memory goes into the right socket and in the right orientation? Well, if you notice, the notches on the DDR2 and the DDR3 are in different positions. So by altering the position of these notches, these keyways, they try to make sure that you can't plug it in backwards. But even with notches like this, I still come across burnt memory pins fairly frequently when people try to install memory and they don't know exactly what they're doing. So in any case, when you are installing memory, take care to make sure it's fully inserted in the socket and that it's in the right orientation. Well, I hope you've enjoyed this look at PC memory types and technologies throughout the years. In this segment, I wanted to talk about the latest processors and chipsets and kind of what's going on with these components. What are the latest advancements and features? Now, when we talk about processor, everybody knows what that is. That's the brains of the system. What do we mean when we say chipset? Well, the chipset is the circuitry on the motherboard that interconnects the processor to everything else. It's kind of like, I think of it as the central nervous system, the spinal column, you know, it carries the data to and from the processor and to every other component in the system. Now, traditionally, the way systems have been designed, we had the processor and a two-chip chipset. Shown in this diagram here, the processor's on the top, and the two-chip chipset is here with what we call the north bridge, or memory controller hub, and the south bridge, or I/O controller hub. And, you know, like the names imply, the memory controller hub typically or traditionally had the connection to memory. So in other words, the memory modules would be connected to this middle chip here. And then the problem with, I don't know if it's a problem, but that design means that any data that would go to and from memory had to go from the processor to the memory controller and then out to the memory modules. Well, AMD in 2003 with the Athlon 64, in addition to originating 64-bit technology, they also originated something that was sort of revolutionary. They moved the memory controller from the north bridge into the processor. So now, instead of connecting the memory modules to, you know, the north bridge and then having that data have to travel to the processor, now it's connected to the processor directly. Intel has recently also adopted this architecture in the Core i-series processors. So the Core i-series now in 2008 also have the memory controller built in. Now some people would say, well, you know, geez, AMD had that, you know, in 2003. Why did Intel take so long? Weren't they at a disadvantage? Well, you might think so, but not actually. See, the real deal is that when a processor accesses memory, it only needs to talk directly to the memory like about 1% of the time of operation. That's because of what we call the cache, the level 1 and level 2 cache that was built into the processors. Now, in another segment, I talked about, you know, processor technology and how the cache originally had been on the motherboard and then was moved into the processor, built right into the processor die. That was true with level 1. The first processor to have level 1 cache was the 486 processor. Level 2, that was the Pentium Pro or 686, which then became known as the Pentium 2 and Pentium 3. Those processors had the level 1 and level 2 built in. Well, more recently, processors now have level 3 built in. That's kind of one of the new advancements. The latest AMD Phenom processors and the Intel Core i-series processors have now 3 levels of cache built in. And because of this cache intercepting calls to memory, the fact that the memory controller was, in a separate component wasn't that much of a disadvantage. Well, finally, Intel has gotten on the same bandwagon as AMD with that. So in this example of a Core i series system with an LGA 1366 socket, we can see that the memory is now directly connected to the processor. And this example uses triple channel memory, which means 3 memory modules at a time simultaneously are being talked to. So we have extremely high bandwidth. A lot of data can flow there. Now, if this north bridge component, used to be where the memory controller was, and now that's been taken away, well, what else does it do? Well, it's also acting here as the interface to video. So when you plug, your video cards into the slots on the motherboard, they are connected now to this what's called an I/O hub, and then the data travels to and from the processor. So we still have an intermediary with video. Now the south bridge component in motherboards has been pretty steady in its functions for many years now. We have connections to things like audio. We have all of our hard disk, our serial ATA or parallel ATA connections in some cases. We have USB. This particular chipset supports 12 USB ports. We have PCI Express bus slots. These are the slots other than video that you would plug cards into. We have things like Ethernet controllers, the motherboard ROM. All of those devices are connected directly to the south bridge. Then data has to travel from the south bridge to the north bridge and from the north bridge to the processor. Well, more recently, also in some of the Intel Core i-series processors, they've eliminated not only the memory controller, but eliminated the entire North Bridge completely and gone to a two-chip design where we have the processor and a single chipset. Now they've simply called this the platform controller hub. It's basically the South Bridge because the North Bridge has been taken away. So this chip does all the same functions as the South Bridge did in other motherboard designs. But now what we have in the certain models of the I-series processors, we have not only the memory connection, again our memory modules will be connected directly to the processor, but we also have the video connection, and that's interesting. By building the video connection into the processor, Intel will be able to sell processors with built-in video, as well as still have slots on the motherboard where you can plug video in. So Intel is getting into the video game even more strong than ever. Instead of having the video built into their chipsets, it's now being built into their processor. So not all of the processors, but some of the models. In particular, some of the lower-end models will have video built in. So that's an example of some of what's going on in the motherboard and chipset area. And as I mentioned also, the processors are now having level 3 cache built in instead of just level 1 and level 2. The other thing that's happening is the technology is becoming more tightly packed. We have processors that have gone from 65 nanometer spacing down to 45 nanometer spacing and now down to 32 nanometer spacing. So we're able to pack more and more transistors into less and less space. Now, what are they doing with are they making the chips smaller? No, actually what they're doing is, this is where we have the ability to have the cache. The level 3 cache was made possible because the rest of the components in the processor became so much smaller. So, to summarize, what we've got here is the migration of the memory controller into the processor itself. That's been happening in both AMD and Intel. And in some of the latest Intel processors, the video interface being migrated directly into the processor. And also, all of the new processors have level 3 cache. Finally, another thing to say is that processors have been adding more and more cores. You know, it used to be all processors were single core. Then we had dual core processors. Then quad core processors, 4-core. Now we have up to 6-core processors coming. And quad core is kind of becoming mainstream. In fact, I wouldn't even consider a single core processor for a system anymore unless it was a special low cost or a very simple need system. Dual core has kind of become the basic, and quad core is even become mainstream. So these have been some of the advancements in both motherboards and processors and chipsets over the last few years. Hi, I'm Scott Mueller. Welcome to the video for the 19th edition of Upgrading and Repairing PCs. This new edition represents a landmark 20th anniversary since the book first came out, making it both the longest running and most popular PC hardware book in the world. I would like to say a special thanks to all of my loyal readers, and I hope to continue working on all of the books and videos in the Upgrading and Repairing series for the next 20 years.